functions and logarithms. Alright, well, let's get started right away. Inverse functions, by the way, in logarithms. I said functions. Let's get started right away. The first thing we're going to do is go over one-to-one. If something's one-to-one, you can read the definition in front of you. What basically it means is you're going to have functions both ways. As you can see in the two graphs in front of you, both of these are functions. And you can tell by the vertical line test. If you make a vertical line anywhere, it only goes through 1 point. But only one of these are one-to-one. One-to-one basically means it's a function both ways. Well, this first one is a function. Because if you make a horizontal line, no matter where you make it, it only goes through 1 point. Over here it's a little bit hard to tell. It looks like somewhere around the origin it may be horizontal, but that is not horizontal. But yes, this one right here is one-to-one. Unfortunately, the second one is not one-to-one, because if I make a horizontal line right over here, you can see it goes through 2 points. So this one is definitely no. I don't know where I got that extra n from, but it's definitely no. It is not one-to-one. So that's kind of easy to start out. You can read the exact definition from what we have. Alright, second thing we're going to do is go over and figure out composite functions and deal with, well, we've dealt with composite functions already. What we're going to be dealing with is also telling if something is an inverse. And if something is an inverse of something else, then both the composite functions f of x and g of x of x is equal to 1. So, I'm sorry, not equal to 1, is equal to x. If you look on the very right side, I have a line y is equal to x right here. I'll put that in green. What I'm going to do is draw the inverse function. We've learned inverse functions in previous classes are reflections along that line. Well, what I did is I made an inverse function of so it's a reflection along that line. So this original line right here, this blue line, is a reflection on that. Both of those are functions, and it's a reflection along the line y is equal to x. And you can see, for instance, let me put two dots on here. If I grab the point -2, -3, which would be about here. Well, -3, -2 would be its reflection. It's not perfect in my graph because it was a little bit sloppy, but you get the point. Alright, so what we're going to do is find the inverse. Just to review make sure it's inverse by showing it graphically and also showing that f of its inverse of x is equal to f of its, well, you can see it in front of you. Make sure both of those are equal to x. So first place is fine. What I always do is use y and x. I use y is equal to 3x minus 2 to find the inverse. And I'm going to switch the variables. I have x is equal to 3y minus 2, and I'm going to solve for that, add 2, and divide by 3. So y is equal to x plus 2 divided by 3. To write its inverse, you should always put a -1 kind of like as an exponent. So that means the inverse of f is equal to, I'm going to simplify this one away, 1/3 x plus 2/3. Alright, so first I'm going to graph the original function. I'll graph the original function, I'll graph it in black. So 3x minus 2, and then up 3 to the right 1. Well, here's my original line. Now my inverse, since I came up with that, I'll put that in blue. So plus 2/3, and up 1 to the right 3. 1 to the right 3 would be about there. And those are inverses of each other. You can see the reflections on the same line, but I didn't prove that they're inverses. To make it a little bit easier, I'm going to call the second one g of x, because I want to prove that f of g of x, I'm just going to write, and g of f of x equals x. So first thing I'm going to do is take f of g of x. And so that's f of 1/3 x plus 2/3. I'm going to plug that in for my original x. So that's 3 times 1/3 x minus 2. I'm sorry, plus 2/3 minus 2. Distribute that. That's 3x plus 2 minus 2. That's equal to, oops, that's just x, not 3x. That's equal to x. So I proved it the first way. Now I'm going to prove it the second way. I'm going to find g of f of x. I actually have to run out of room, so I'm going to take g of f of x. Alright, plug in f of x. Well, f of x is 3x minus 2. So that's, I have to find g of 3x minus 2. Now I use my function g. I take 1/3 times 3x minus 2 plus 2/3. So distribute that. That's x minus 2/3 plus 2/3, and of course that's equal to x. So I was able to prove that they are inverses. I looked at the graph and I was able to do that algebraically. What I'm going to do is I'm going to go over one more that's a little bit tougher, and then I'm also going to prove one that is not, you can't, if you found the inverse, well, it's not a function, because that's what our goal is going to be, to do our homework. Alright, first one, it says find the inverse. So what we're going to be doing is, if I find h of x, and I'm going to actually rewrite that as y is equal to x plus 4 over 2x minus 5. And I'm going to switch the x's into y's, so x is equal to y plus 4 over 2x minus 5. Alright, so, to y minus 5. I have to solve for y. So when I'm going to come up with x times 2y minus 5 is equal to y plus 4. Alright, my goal is to solve for y. So what I'm going to do to start out is, well, first place, this is where some people get confused, so I'm going to spend a second just looking at this. So what I do is, right now, I have the correct item, but what I want to do is I want to get the y's by itself. If I distributed that, what I'm going to get is 2xy minus 5x is equal to y plus 4. Then what I'm going to do is factor a y out, because that's what I want right over here. Actually, I'm going to get the y's on one side by themselves, so 2xy minus y is equal to 4 minus 5x. Factor out a y, as I said earlier, so 2x minus 1 is equal to 4 minus 5x. What I came up with is inverse, or y, is equal to 4 minus 5x, and I can divide by 2x minus 1. So I was able to get y by itself. I'm going to write it correctly, though. So I'll write h inverse of x is equal to 4 minus 5x over 2x minus 1. So I came up with its inverse. What I'm going to do is I put these on my graphing calculator. I'll graph those to start out. I'm only going to do it one way, basically for time's sake. What I'm going to do, and let's just to make it easier, I'll call this f of x, and I'll call this g of x. I'm only going to solve it one way. On your homework, you are going to have to solve it both, but you'll get the point in the presentation. Well, first thing I'm going to do is find f of g of x. That's all I'm going to do. And I'm going to prove that's equal to x. You would have to prove it to prove that it is an inverse then. So f of g of x, let's see. So I'm going to find f of, this is going to be nasty, 4 minus 5x all over 2x minus 1. Alright, now what I'm going to do is put that entire thing in place of my other one. So I'm going to find, that is going to be x plus 4. I'm going to take 4 minus 5x plus 4 all over 2x. Oops, I still goofed up, so let me go back. Let me erase that so people don't get confused. I did make a mistake. I have to put that whole thing in there. So I have to put 4 minus 5x over 2x minus 1 plus, so 4 minus 5x over 2x minus 1. Looks like I got a common denominator on here. So hang on a second. Yeah, that's right. Plus 4 all over, and then 2 times 4 minus 5x all over 2x minus 1 minus 5. Well, I need to get a common denominator. So to put these together, what I did is I multiplied this one by 2x minus 1 and this one by 2x minus 1. Same thing over here. I put all those together. What I'm going to come up with, and after playing with it for a little bit, I came up with, let's see, what am I going to come up with? So let's see, had a common denominator, 4 minus 5x plus 8x minus 4 on the top, divided by 2x minus 1. Then I'm going to put over here, see if I distribute that, that's 8 minus 10x plus 5 all over 2x minus 1. Alright, for sure I can see the 2x minus 1's cancel, without a doubt. So what I'm going to come up with, looks like 13x because the 4's cancel, over, looks like the 10x's cancel over 13. Oops, there's a 13x there. That's equal to x. I was able to prove that's equal to x. So I found h, what I really found was h of the inverse of h is equal to x. That's what I was able to do. What I'm going to do is I graph these on my graphing calculator. Well, h of x, which was the top one, it had a horizontal asymptote at 2.5. And let's see, it had a, so let's see if that is right, yes, a 2.5. So this one kind of looked like here. Alright. Now when I went to graph my other one, which is this part right here, what I came up with, this one had a horizontal asymptote at 1/2. What it came up with is, see if I can do this correctly. This one was a little bit higher. Actually, that other one was a little bit higher. And this one looked more like here. And you can see that both of those are that graph is not perfect, but if you looked at that on your graphing calculator, which I wouldn't have you graph that one by hand, you wouldn't have in it. You'd see that both of those are functions. The last one I'm going to do is go over to find the inverse. And you're going to see on your homework you're not even going to have to deal with the second part. Well, first one, I have y is equal to the natural log of x squared. My goal, once again, is to find the inverse of it, which there is an inverse, you're going to see, but it's not going to be a function. Because if I take, right now I have x is equal to the natural log of y squared, I'm going to get rid of the natural log, so I'm going to take e to that power, because I know the natural log and e are inverses of each other, so I'll have e to the x is equal to y squared. Alright, my goal is to solve for y. I'm going to get y is equal to plus or minus the square root of e to the x. Make sure I'm doing that right. Yep, plus or minus square root of e to the x. Well, there's a problem. If you put that on your graphing calculator, you are going to come up with, and make sure you are going to come up with a graph that's not a function. Just so you can see this won't be exact, but e to the x we know looks like this. The opposite of e to the x is going to, whoops, that's not right. E to the x should look like, I have that backwards. And the opposite of e to the x, well, you can't take the square root of both of those, so this one right here would not be a function. You can check on that, so you would not even have to go through that second part. Alright, what we're going to do is go on to what we have to start out. When solving equations algebraically, hopefully this is going to be a strength of yours. I'm going to go over one easy problem, two kind of tough problems that you're going to have to deal with, and we'll see what we have to do. Alright, well, first one is pretty straightforward. You can probably do this in your head. You can probably see that x is equal to 4, but I want to solve it algebraically. So first thing what I want to do, since I have 2 to the x, I'm going to use logarithms. I'm going to take the log base 2. The reason I'm taking the log base 2 is because the base on this 2 to the x is 2 is equal to the log base 2 of 16. Alright, we've learned before if you take the log base 2 and you have 2 to a power, they just cancel them out, so you're going to end up with x. Some people are going to have trouble taking a log base 2 of 16s. Some calculators have those programmed in. If you don't, you're going to have to use the change of base formula, which is log of the 16, or actually log base 10, over the log of 2. What I'm going to do is put in log base 10 here. You don't have to show that, because when you don't show that, we call that a common logarithm or a log base 10. You're going to put that in your calculator. You're going to come up with x is equal to 4. And just an FYI, it doesn't have to be log base 10. It could be log base 3, log base 7, etc. Or even, for that matter, natural log, because the natural log of 16 over the natural log of 2 would also be equal to 4. All right, let's go over another one. Once again, we're going to solve for x. So first thing I'm going to do is divide by 3. Well, 54 divided, because my goal is to get x by itself, is 18. Now what I want to do is get rid of e. So what I'm going to do is, some people make a joke out of it and they say they drop a natural log. And then I'm going to come up with 2 to the x is equal to the natural log of 18. I have no idea what the natural log of 18. I'd have to take out my calculator. But since I'm almost done solving, I'm just going to get the exact answer. I'm going to get x is equal to the natural log of 18 all over 2. Alright, now what I'm going to do is solve the third one. The third one looks kind of tough initially. And it really is. It is the toughest of the 3 problems I'm going over. So first thing I'm going to do is, I notice the negative exponent. I'm going to rewrite this as e to the x, plus, not minus, plus 1 over e to the x equals 2. I have a problem. I can't solve that just by looking at it. I have to get a common denominator. So what I'm going to do is get a common denominator throughout here. So if I put this together, e to the x times e to the x, we've learned when they have the same bases, you add those. That's e to the 2x plus 1 is equal to 2e to the x. This is all equal to, all over, e to the x on both sides. I notice on the left side I had common denominator, so I put those together. Well, I don't have to worry. I can multiply both sides by e to the x, and that's not going to change anything, because we know the graph of y is equal to e to the x. That is always positive. It has to be. So the graph of y is equal to e to the x. It can't be 0. So we don't have to worry about anything being undefined. So I can multiply both sides by e to the x, and they're going to cancel. All right. So what I'm going to come up with is e to the 2x minus, because I'm setting it equal to 0 right away, plus 1 is equal to 0. Some of you can solve this right by it. What I like to do is I like to take out another variable. So I set a is equal to e to the x. So of course this is a squared minus 2a plus 1. You can factor that or use a quadratic formula. Since this is easy enough to factor, I'm just going to take a minus 1 is equal to 0. That's easy enough. But I have to solve for x, not for a. So it's really e to the x minus 1 equals 0. So I'm going to come up with e to the x is equal to 1. And now I'm going to take the natural log of both sides, because I want to get x by itself. So I'll take the natural log, natural log. So natural log of e to the x is x. Natural log of 1 is 0, because that's the natural log of 1. And it does make sense, because basically e to the 0, which is 1, e to the opposite of 0 is still e to the 0, that's 1, and that is equal to 2. So that is the correct answer. You're going to have a problem like that, but it won't come out exact in your homework. Alright. Third thing we're going to do is just talk about this. We've seen this before. I don't want to make these more complicated. Like for instance, when we graphed previously, I graphed, and I'm going to put this on here, y is equal to 2 to the x, and the exponential. And we came up with a graph like this. You can see its inverse is log base 2 of x. And this also fits for the natural log of x. If you graph the natural log of x in your calculator, you're going to see it's very similar to the log base 2 of x. And what we're going to do, so in this, by the way, these a is any number. All these fit about the same. So what I would do if I was graphing this, I'd probably deal with, whoops, I don't know why it made that. I'd probably take the log base 2 of 2. Well, I know that's 1. So if you see 2, that was 1 right there. All right. And if you graph all of these, you can't come up with a log of a negative. For instance, we learned log base 2 of 0 is undefined, and you can't also do that with a negative. So that's why everything is to the right of the x-axis. I'm sorry, the y-axis. So what we're going to do is key on this one, this graph right here. We're going to look at how things change to start out. The first place is start with a domain and range of here. The domain, you can't come up with a negative, and that's what we talked about, so it's going to be from 0 to infinity. The range, for sure you can see it goes forever down. This one is not going to be, it's not an asymptote, it's going slowly up, so this one is either all reals or from negative infinity to infinity because it goes forever up. So we're kind of studying that graph a little bit. Alright, this other graph, because the negative is before that, it kind of makes sense that it flips. So if instead of starting on the bottom and going up, it starts at the top and going down because everything is becoming a negative. So it's the opposite of what you have. That makes a lot of sense, and that's what that negative before that is going to cause. So let's go over the domain and the range. Well, in this case, the domain is it's going to be exactly the same because it starts on the left side at 0, and the right side it goes to infinity. The range, you can put all reals, or because that's up and down again, it's the same as before, and that's what we're going to. That's what you're going to come up with. All right, and then what I did is I put a negative log base 2 of the opposite of x, and I graphed that. Exactly what happened before happens again. So what I noticed is, what the graph does is flips. It's a reflection on the y-axis. Surprise, surprise, that has happened in previous graphs that we went over. So what I'm going to do is look at the domain and range on here. By looking at my graph, my domain looks like it's negative infinity because it goes forever, but it stops at 0. My range, oh boy, there's a pattern here. Looks like it's all reals. If you're noticing a pattern, and that's I'm going to go over that before I go over look 1, you're going to see something is happening again. You have x minus h plus k. We learned if you put a negative before that, so if you put a negative, it's a reflection on the y-axis. Surprise, surprise, that's what happened. If you put a negative in front of this part, for instance, if there's a negative right there, what it does is it flips. It flips, so that first one, I'm sorry, this first one we put a negative right there, it wasn't a reflection, but I said that wrong. It just flips, it's a reflection on the x-axis. This right here, this is a reflection on the y-axis. So what we're going to do is put both of those together. I didn't say that right, but you can see that in front of you. Hopefully you, what I'm going to do is see what this does. I'm going to come up with y is equal to 2 times the log base 2. I'm going to first write it right. I'm going to take out a negative from here. And if I took out a negative, that's really x minus 1 plus 4. So I took out a negative there to start out. Well, the 2 just makes it steeper. All right. So, but I had a negative here, so I'm going to go to the 1 on the left and see what happens. Well, you can see it kind of fits the pattern of this lower left part, except it's a little bit steeper, and that's what that 2 caused it to be as steeper. Then I went, looks like, to the right 1 and up 4. Alright, so what I want to do is kind of find the domain and range. Well, the domain and range, start with the domain. Domain is really the only thing that's going to change. Instead of going from negative infinity to 0, this goes from negative infinity to 1. Why? Because everything's shifted to the right 1 because of this right here, and that's exactly what we expected. The range goes forever up and down, so that's not going to change. That is going to be all reals or from infinity to negative infinity to infinity. But you're going to notice a lot of the graphs follow that same shift pattern. Hopefully you remember that shift pattern from that trigonometric unit. Alright, the last thing that we're going to go over are the applications. And this isn't going to take too long. This is one of the things I did not cover in a previous unit and how to apply that. So what we're going to do is use this formula so we can figure out how to use logarithms, and that's going to be our goal. If we have 2,000 students right now, I want to know how long it's going to take to get to 2,100 students. Starting then by using that formula is going to be 2,000. That's y sub 0. Ending 2,100. That's y. And I'm going to come up with 1 plus r, and we always write that r as a decimal. If you remember, I want to know how many years. First thing I'm going to get is 2,100 is equal to 2,000, and then 1.02 to the t power. My goal is to solve for t, so first thing I'm going to do is divide by 2,000 on both sides. Alright, that makes sense. And if 2,100 divided by 2,000 is 1.05. Put that on my calculator. I sure won't do that in my head. And I have 1.02 to the t power. This is where you have a lot of options. I like to use the natural log, but you can use a log or common log, any logarithm, because what my goal is, I want to get this to the front. So what I'm going to do is use a natural log. If you took on both sides and you use the common logarithms or just took a log of both sides, it is correct. You can use log base 10, log base 2, log base, I don't care. It's going to work as long as you're consistent on both sides, because what our goal is to get that t out front. So I'm going to rewrite that as a natural log of 1.05. We learned by logarithms we can write this out front, so t times the natural log of 1.02. I have one more step to solve, so I'm going to get t is equal to, I'm dividing by the natural log of 1.02 on both sides, so I'm going to take the natural log of 1.05 divided by 1.02, and those are two separate logarithms. Make sure I did that right. I'm going to look back. So 1.05 divided by 1.02. I put those both on my calculator. I came up with 2.4638. So 2.4638. I want to know at the beginning of the school year, so really it's a, I know it says 2.4638. Since this isn't worded very well, if you put this many years, I'd accept it, or 2.464. I'd also accept if you put the third year. So the third year, and it's basically 3 more years at the beginning of 3 more years that we're growing, no problem, because the second year we won't quite have 21. The third year we would have over 2,100 students, so I'd take both of those. Alright, hopefully that helped you a little bit in a review of logarithms. Hopefully you're successful on your homework assignment. Have a great day.